want to get him in here. Okay, you should be seeing a screen. The computer screen. Let me do YouTube music here. I'll do one with we'll do space music because that's what I had last night. It's kind of creepy. 1 hour of epic space music. Gotta love it. Right now I have no... Okay, so we do have sound. Alright, so I've got sound. That works. Do you have sound on your end, Margaret? Or I did have sound? Let's give it a whirl here.
Good demo? Yeah, good.
My name is Dane Walters, and I'm a stuntman who does tumbling, gymnastics and parkour. I'm attempting to run the loop, because I've seen people do it on a skateboard before, I've seen people do it on a BMX before, but no one's ever tried it on their feet, so it'd just be nice to be the first guy to actually run it. It looks a lot bigger than what I thought it was going to be. Yeah, I must admit, not the easiest thing I've ever done. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
Basically boils down to this centripetal force. You need to keep on accelerating. So you need to reach a certain speed. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour.
That it?
That's it.
Okay. 3, 2, 1, go. 17.
5'11". Easy 5'11".
Can somebody show him that one back? Well, this one's it. I know I've said that 3 times now, but this one is it. But I'm close, I reckon I'm close. Getting close. You can't really go any further until you take the match. Yeah, let's get rid of him. Let's go for it.
So hopefully, if you've ever played with Legos, or not Legos, but Hot Wheels, many of you, because I've done it as well, many of you have done the loop-the-loop, or gotten the Lego car to do the loop, or the Hot Wheel car to do the loop-the-loop. See if I can get this to do what it needs to do. There we go. Thinking about it. Okay. Okay, that's weird. I'm getting an interesting. Okay. Let's see if I got. All right. It's just that it's heavily zoomed in. So now I've got it. All right. So we're going to actually do a calculation. We're not going to use the centripetal force calculation that she had used, but we'll see that one again. We're going to actually do the Hot Wheel car version of it. So what I've got is a loop. So we've got this loop here. we have a car or a box or whatever that we're going to slide through. And we're going to use a conservation of energy problem to do this. So this is my height here, okay? This is the radius of my circle. And we want to make sure that we've got the box up here as it comes down, and it's going to do the loop and come at that point. And we want to find what the velocity has to be. So we want to find the velocity here, just like she had done in the calculation, but we're going to use conservation of energy to make sure that things stay on the loop. And if you've ever done your Hot Wheel car, you know that some of them make the loop and some of them don't. You also have some of them that fall in there. Some of them don't even make it up to that spot. Some of them fall when they get to that spot. And so what we're going to do is we're going to use conservation of energy to get there. So we want to know at this point, this is point A and this is going to be point B. So the energy at A has to equal the energy at B. And at A, we know we can have potential energy and we can have kinetic energy. And at B, we're going to have potential energy and we're going to have kinetic energy. We want to know what we've got to get there. So potential energy at A is going to be our mgh. My kinetic energy at A is 0, because that's what we're starting out. My potential energy at B is going to be mg. Now r is the radius, so the height here is going to be 2r. So that's going to be 2r, the radius of my circle. And then my kinetic energy is going to be 1/2 mass times the velocity at b squared. And we're solving for b. So if I want to know my velocity that I have to have this work, we want to go ahead and rearrange it and solve for b. So I've got mgh is equal to mg2r plus 1/2 mvb squared. Masses can all cancel. So I've got gh minus gr, or 2r, don't forget the 2, is equal to 1/2 vb squared. So I'm going to multiply by 2. So I've got 2gh minus 4gr is equal to b squared b. If I take the square root, I get the square root of 2gh minus 4gr is equal to b. And that would be the velocity that I'd have to have in order to stay up at the top. Or you can rewrite it and clean it up. 2gh minus 2r. B up there. Now, one of the interesting things is our guy who did it in the video, he actually came running straight into it. If you're on a skateboard, trying to generate enough velocity on the skateboard in order to get up there is a little tough. Most of your skateboarders are going to come in on a ramp. Skateboarders can come in on a ramp. Your Hot Wheel car is going to come in on a ramp. You've got a variety of things to come in on a ramp in order to get the velocity to actually work. Of course, his challenge, one of his challenges, because you saw that he actually had a challenge that when he was doing it. So if I'm coming in, I'm looking at my person. As he was running through, we had him setting up like this. he was actually having to change his center of mass each time in order to get around the piece. So he actually had to rotate his body a little bit, and that is actually going to make it a bigger challenge because he's actually going to have to move in order to have it piece work through it. So that's one way we can use conservation of energy in order to get the problem worked. And that was one of the conservation of energy problems I kind of wanted to look at. We're going to look at another conservation of energy problem. So it was good to start with a fun one. Actually see physics in action and play with the physics a little bit and do something a little bit more fun and just doing weird problems. So one thing that we can do is what we call the ballistic pendulum. Okay? And in the ballistic pendulum problem, if I've got a pendulum, okay, and we used to do this as a lab, but can't do those things anymore. You know how it goes. We used to have a wad of clay on the pendulum, and we would send in a BB and have the BB hit the pendulum. And you can use this because it's going to go up as it curves up, and it's going to reach a maximum height. And this is fairly easy to measure. Speed of my BB or the speed of my bullet or something else is not quite as easy to measure. I can use the Doppler effect to measure it, but it's not something that I can readily, easily measure. And so one of the ways I can measure is to do something like this to look at conservation of energy. So I'm going to have a bullet, and I'm going to use a bullet. Okay? I'm going to use a bullet, and I'm going to have this bullet be, we're going to call this bullet 5 grams. And we're going to call this target 500 grams. And this time I'm actually going to say that we actually measured the height. And the height that it actually measured, we're going to say it went 0.5 meters high. So I'm totally deviating from my notes. Okay, totally deviating from my notes, but we're gonna see what we get because I don't know those numbers at all. So when it hits, so this is the before because we're doing momentum. So the momentum before has to equal the momentum after. This is an inelastic collision. And in an inelastic collision, I have total energy is conserved. So I have total energy conserved. I don't have an elastic collision. Elastic collisions have the special case of kinetic energy is conserved, and we're actually going to use that special case here to do another problem. But for this problem, it's inelastic, and we're going to have total energy conserved. But I have my momentum conserved. So let's see what we get. My markers are dying. So I'm dropping my markers. All right. So the momentum before, we've got total energy. So let's look at this part of the collision. Okay, we're going to look at the after part. Now on the after part, my bullet is now part of my target. And it's going to raise up to our height h. So the total energy before has to equal the total energy after. The energy here is potential energy plus kinetic energy. And at the top, kinetic energy is equal to 0. So at the top, I just have potential energy, which is mgh. Down here at the bottom, I have potential energy plus kinetic energy. But at the bottom, potential energy is equal to 0. Because I'm at the bottom of my swing. Now I can rewrite this so that down here at the bottom, I just have kinetic energy, which is 1/2 the velocity of my pendulum, and I'm going to use P for that, squared, is equal to mgh. Masses cancel, but we want to look at this mass for a second. This is going to be the mass is going to equal the mass of the target plus the mass of the bullet. Because I'm going to need that later, but right now I don't need that because my mass here is the same mass there, so those cancel out. So the velocity of the pendulum is going to be the square root of 2gh, which we've seen now a lot of times. We've seen that actually a lot of times. So if I know the height, we know the velocity of the pendulum, so that's going to be 2g times my 0.5. And if I plug that into the calculator, I actually brought my calculator today. Yay! 2 times 9.8 times 0.5. Square root. It's going to give me 3.13 meters per second. We want to look at the units here. Gravity is in meters per second. My height is in gravity is in meters per second squared. My height is in meters. So I got meters squared, second squared. Under the square root, I end up with meters per second. So we've done that part correctly. Okay, so I'm going to leave my handy dandy picture here. So one of the things that we now know and we can add to our picture is that my velocity is 3.13 meters per second. So now we're going to do the collision part. Okay, the collision part. So on the before side, I've got the mass of the bullet, the velocity of the bullet, plus the mass of the target, velocity of the target, is equal to the mass, and this we can do little b's here, before. Now I've got the mass of the bullet after, the velocity of the bullet after, plus the mass of the target after, the velocity of the target after. Now when I end up after the bullet is in the target, so the velocity of the bullet after has got to equal the velocity of the target after. And we calculated that, the velocity of the pendulum, from our conservation of energy. So from my conservation of energy, I've got that, and we now know what that is. That's 3.13 meters per second. So now, if I look at it, I've got the mass of the bullet, and the mass of the bullet before and the mass of the bullet after is the same, so I can ditch the subscript. I've got the velocity of the bullet, but when I'm here before the collision, this is at rest, so that's 0. Because it's just sitting there. That's just sitting in place. It's not doing nothing. Not doing nothing. It's a happy camper. And then over here, now I've got the mass of the bullet, and we're going to do the velocity of the pendulum, plus the mass of the target, velocity of the pendulum. But now I'm going to separate that out just to make calculations a little easier. And if I'm solving for the velocity of the bullet, I get the velocity of the bullet is equal to the mass of the bullet plus the mass of the target divided by the mass of the bullet times the velocity that we know. And we said that this was 5 grams, so this is 0.005. Mass of the target is 500 grams, so that's so we're all in kilograms. Or I could have stayed in grams because I'm dividing it out. But the mass of the bullet is 0.005, and I get 3.13 meters per second out there. And when I plug that into the calculator, this says this is traveling 101. That's 101 is that ratio, 3.13 meters per second. Gives me 316 meters per second. That's one way to tell how fast something's going. All right, we'll come back to that one. I'm going to do, before I do the more complicated one, I'm going to do one that's in 2 dimensions so that you guys can get your homework going. So we're going to have, I'm going to write out the problem here. We have 2 masses. Mass 1 is going to be 5 kilograms. Mass 2 is going to be 10 kilograms. Mass 1 has an initial velocity of 2 meters per second in the positive X direction. Mass 2 has an initial velocity of 4 meters per second in the positive Y direction. These are going to collide. And they're going to stick together. What's the final velocity? Okay, so this is a little different because so far we've only looked at collisions in one direction. We haven't looked at collisions in 2 directions or 3 directions at all. So basically what I have is I have mass 1, and it's in the positive X direction, and it has a velocity of 2 meters per second. I've got mass 2, and it's coming in at 4 meters per second. And we know a couple of things, okay? If we think about what happens, this is the before part. They're going to come together. They're going to stick together. And we know that they're going to go off probably something like this. Because I have the larger mass here, the larger speed, reversing this one, and they're going to come off and they're going to go off in another direction. Okay, here's the fun part. We have conservation of momentum. And what happens is the total x and the total y components are conserved. So my x component is going to be conserved and my y component is going to be conserved. So this is going to allow us to do something. Now, I work them a couple of different ways, and so I'm going to show you one way to help you out. Okay, so here's the system. I can create a chart because I know I've got an x and I got a y component. And this is going to be my initial, and this is my final. And one of the things that we know about this situation, and I can draw in my picture, there's going to be some sort of angle here because they've collided together, and I'm going to have some sort of final velocity there. Because they stuck together, my mass final is going to equal the mass 1 plus mass 2. Because they stuck together. Okay? They actually stuck together, and we've got that part. So in the x direction, I'm just going to have mass 1, velocity 1 as my initial. Because my second one doesn't have any x component. It only has a y component. So the y component is just this one. So I have my x, my initial component of my velocity, and my second component of my velocity. Now, if I were coming at it at an angle, I would have to figure those in as well. My final is going to be my mass total, but I only want the velocity final in the x, okay? My second one, I've got the mass total, and I want the velocity final in the y. And we know that the velocity final in the x is going to equal the magnitude of the velocity cosine of the angle. Velocity final in the y is going to equal the magnitude of the velocity sine of the angle. And if I look at it here, that's my x component, and this is my y component. So it's the same way we've been dealing with our velocities all along. So now I can rewrite this. So I've got a nice little handy dandy chart. Initial, final, x, y, m1, v1, m2, v2, and I have m total, v cosine of the angle, m total, v sine of the angle. I have two unknowns. This is an unknown, that's an unknown. Which, it's a good thing because I have two independent equations, so that helps me out tremendously. Okay, so I've got two equations, two unknowns, so I get m1 v1 is equal to m total v cosine of the angle, and I get m2 v2 is equal to m total velocity sine of the angle. So here comes the fun part. I can do a couple of tricks in order to solve for these. One is I can do a direct substitution and solve, but this one will make our lives a little easier because sine of the angle over cosine of the angle is the tangent of the angle. So I get the tangent of the angle. So I can actually do that arithmetic. I'm going to do it this way, so I'm going to rewrite this just a smidge. So I'm going to put m2 v2 is equal to m total v sine of the angle. I'm going to divide it by m1 v1 mt v cosine of the angle. Those are going to cancel out, and I'm going to get m2 v2 divided by m1 v1 is going to equal the tangent of the angle. by the end of the day, I'm going to probably get rid of all my pens. So let's put in some numbers. We said that we M1 and V1 and all that good stuff. So M2 we said was 10 kilograms. V2 is 4 meters per second. M1 was 5 kilograms. And V2 was 2 meters per second, or V1. That's going to be the tangent of the angle. This gives you 40 over 10, which gives you 4 tangent of the angle, which means that my angle ends up being 75.97 degrees. So I know what direction it's going off in. Now that I have that, just pick one. We'll pick, so I've got M1 V1 is equal to the mass total, the velocity, and M1 is the cosine. So now I'm going to solve for V. V is going to equal M1 V1 divided by M total cosine of the angle. So mass 1 is 5 kilograms, 2 meters per second, divided by my total mass, which is 15 kilograms, cosine of my 75.9 or 797 degrees. And if I plug that into the calculator, I get 4.58 meters per second. So we can look at these two-dimensional ones in a variety of different ways. So let's take a mass. So we're going to say that this has a mass of 0.01 kilograms. And we're going to hit this. We're going to hit an object. And when we hit the object, this doesn't move. So the velocity before is equal to the velocity after, which is equal to 0. So I don't have to worry about that. And we're going to have that it's like a pinpoint, so it's not going to affect the direction. And when this happens, this is going to break up into one glob. Okay? And we've got one glob that's going to go off directly in that direction. And then I've got another glob that comes off in some other direction. After we do the experiment, this glob here is going to be 0.006 kilograms. And this one is going to be 0.004 kilograms. So we're not losing any mass. All right, not losing any mass. We're going to hit our target with a velocity of, we'll go ahead and say 50 meters per second. And we're going to say this comes in at an angle, so I haven't drawn my picture just right. So we're really coming in at an angle a little bit off here. And this angle, we're going to say is 10 degrees. And we're going to say this angle is 0. And this one, we don't know. Okay? and we said this is coming in at 50 meters per second. And we're gonna say that this one here, I'm making these numbers up as I go, is gonna be 36 meters per second. And we wanna know the velocity of this particular mass. Okay? We want to know the velocity of that particular mass. So I can do my chart here. Initial, final. My initial one is going to be in the X direction, because I gave you this part, is going to be my 50 meters per second. Sine of 10 degrees, because of where I gave you the angle, times the mass that we had to start with. So this is my mass times my 50 meters per second, cosine of the angle for my initial. The new one, we've got two pieces here. Okay, the final, we've got two pieces. So my final in the X direction, give myself some room here, is going to be the mass of part 1 times 36 meters per second plus the mass of part 2, and it's going to be its velocity cosine of its angle. The final Y, part 1 only went off in the X direction, so I don't have to do it. So I've got the mass of part 2, sine of the angle, velocity times the sine of the angle. So now I get my two equations. So I get the initial mass, 50 meters per second, sine of 10 degrees is equal to 36 meters per second, mass of part 1 plus the mass of part 2, velocity cosine of the angle. Then I get the initial 50 meters per second, cosine of 10 degrees is equal to the mass of part 2, velocity, sine of the angle. This one's going to be a little trickier to do from a mathematics point of view, because I can't do my little math trick to get my tangent of the angle, but I still have two equations, two unknowns. Because I can get a number here, I can get a number there, and direct substitution. So it works the same way. It's going to work the absolute same way. Okay, it's time for the fun one. All right, so hang on, I gotta get my handy. Let me get my question. I think everybody's seen this trick. I can't demonstrate it, so I know people who can, but that's not me. Got a basketball, and I have a tennis ball. Okay? And we've all seen this demonstration that we drop the basketball and the tennis ball at the exact same time. It's going to hit, it'll hit the floor. The basketball is going to rebound, and we see the tennis ball shoot way up. Right? We see the tennis ball shoot way up. We've got the mass of the tennis ball The mass of the tennis ball is going to be 57 grams. My mass of my basketball, I think that says 590. You double check. Yep. Mass of the basketball is 590 grams. We are dropping it from the same height. So the height that we've got is going to be 1.2 meters. And we're going to go, we want to know how high the tennis ball goes. Okay? We want to know how high it goes afterwards. So we got to think about this one just a tad. Okay? Because when it falls, the tennis ball is falling, and the basketball, just after it hits the floor, bounces back up. But they're dropped from the same height. So our initial velocity of the tennis ball is going to equal the negative velocity that we have of the basketball. And the initial velocity of the basketball is going to go positive because they've been dropped from the same height. Right after the rebound, the basketball is traveling with the same velocity. And I've got the part that goes up and it's coming down. So this is one of the key parts to solving the problem. Still conservation momentum. So momentum before has got to equal momentum after. Okay. So now we're going to get a little complex here. All right. We're going to get a little complex. So I got the mass of the tennis ball, velocity initial of the tennis ball, plus the mass of the basketball, velocity initial of the basketball, has got to equal the mass of the tennis ball, the velocity after the tennis ball, plus the mass of the basketball, the velocity after the basketball. Okay? Now, when I do that, initial, making sure I got everything here. It's always the fun part, just get there. Also final after, so I got those parts. Okay, so I want to have my after, and we got my initial. So I'm going to have the mass of the tennis ball, my new velocity, that's negative, plus the mass of the basketball velocity is going to have my mTVAT plus mVVAB. So now I get mv minus mt. Velocity is equal to mTVAT plus mVVAB. We're going to use, in order to solve this problem, that if this is an elastic collision. And if I have an elastic collision, the kinetic energy before has to equal the kinetic energy after. Okay? This is my criteria for an elastic collision. Okay. We're going to use that. Now, when you do this, you can go ahead and go through the 1/2 mv squared of the tennis ball plus the 1/2 mv squared of the basketball. And I'm going to leave this for you guys to play with because this is one of those criteria with a little bit of algebra, okay? It's going to equal 1/2 mv tennis ball after, velocity of tennis ball after, plus 1/2 mv of basketball after plus 1/2 mv after squared. So you can play with this, and I'm going to leave it to you because the funny part is when you see in a textbook, you'll see a couple of quotes. One says with a little bit of algebra, just assume it's going to take you about a page to do. One can be easily shown that's like pages and pages of algebra. And then the other one is it can it's obvious that. Well, if it's obvious that, we always say it's an act of God because the mathematics to get there is almost impossible. But what happens is that if you play with this, what you end up getting is that you get the velocity of the tennis ball before minus the velocity of the basketball before is equal to the velocity of the tennis ball final minus 2 times my initial velocity. So you'll end up getting that, and you end up playing with it a little bit, and you end up to get combining those two equations. You get the mass of the tennis ball, the velocity of the tennis ball final, plus the mass of the basketball, the velocity of the tennis ball final, minus 2 of the velocities is equal to mb, which is the mass of the basketball, minus the mass of the tennis ball, velocity initial. Solve for the velocity of the tennis ball, and it works out to be 3 the mass of the basketball minus the mass of the tennis ball divided by the mass of the tennis ball plus the mass of the basketball gives it times my velocity. And we've already seen this one, because if I'm starting at a height, right, mgh is at the top, 1/2 mv squared at the bottom. If I solve for v is going to be the square root of 2gh. Plug that back into there, and you get the velocity of the tennis ball final is 3 times the mass of the basketball minus the mass of the tennis ball divided by the mass of the tennis ball plus the mass of the basketball, square root of 2gh. And if I plug in my numbers, I get 3 times 590 minus 57. Divided by 5790 plus 57. I've got square root of 2gh. I'm going to leave that right there. So if I do that calculation, 3 times 590 minus 57 divided by 590 plus 57 gives me 2.6 times that square root. Now you can see why I did it, because we're solving for h. And you can go back using that this v is v tennis ball final squared is equal to tennis ball initial squared plus 2a change in y. And if I do that, I end up with, on this side, v squared. Hang on, I'm going to do this a little cleaner. There's my v, tennis ball final is equal to 3mb minus mt plus mb times my velocity, which we got to be 3mb minus mt divided by mt plus mb square root of 2gh. Okay, use the v squared is equal to v initial squared plus 2a delta y. And I get my delta y is going to equal vy squared minus v naught squared divided by 2a. And what works out here is you end up with my, at the top, this is 0 minus v y squared 2 minus g, and that is going to equal, and I put this in 3 mb minus mt m plus mb squared 2gh. And then you solve for h. When you do that, you get change in y, which is h, is equal to this lovely squared. Oh, this, sorry, that change in y is the height that we want. Is this mass, the mass term squared, times the height we dropped from. And that, when you plug in those numbers, you get 8.41. And this is just an ookie algebra problem. Just a ookie algebra problem.
Just one more.
Uh-huh.
What's that say? It's right to the right of the 0 minus velocity.
This?
One more to the right.
This one?
Oh, sorry, you're the other one.
This way?
One more.
This one?
Yeah, that one.
This is my mass term squared,
Oh, okay.
2gh. Because if I'm doing this velocity, I gotta spur it to get in there, and that's what happens to it.
All right, thank you.
Okay. All right, I'm sure brains are full. And when you do the basketball problem, brains get full. Dana, I gotta talk to you. All right, I see you guys Friday. We'll probably start rotational motion on Friday. But the test will